Um, with some luck today, we'll finally learn what is elliptic stable envelope, and it's going to be just we can then get started. It'll be the very beginning of the course. So I would remind everybody what was the setup. The setup, we had some algebraic variety x algebraic variety. With an action of a torus. And the way we were thinking about that, this algebraic variety, that was supposed to be, it was some moduli back here, and these were subglobal symmetries, which we could use to kind of use an external field. But maybe this is, if you remember this motivation, that's fine. If you don't remember it, it's also fine. And so with this picture, we're associated with a certain like a phase diagram. So maybe I'll draw it here. And that phase diagram was taking place in the Lie algebra of A. Those were the variables, those were the masses in this perturbation. So the Lie algebra of A. And then what the diagram, what this was recording, was recording the fixed loci of the different points in this different exponential different points. So for example, at the very middle, maybe I'll just, I draw this picture almost every lecture. And so in the very middle here, this is 0. The fixed point of 0 is just the x itself. And if you take a generic point, you get the fixed locus of a torus. So this takes place. This was taken in kind of the real version of the Lie algebra of A. So if you're, and so and then we would, so this would be, if we want an interface between this phase and that phase, so we wanted an interface, some kind of interface here. I'll just draw it in green. Some kind of interface here. Well, that a choice of its chamber. This is a choice not only. So first of all, I have to have something which is which connects x and the fixed locus, and also a choice of this chamber. That's a choice. So this chamber here is a choice of attracting and repelling interactions. So what would be the interface would look like? Well, we want a Lagrangian. Now, so maybe this is, let's assume this was symplectic. And this torus preserving symplectic form. So we want a Lagrangian. Inside x cross, so this some interface that connects them. And if x was a vector space or in the neighborhood of a given fixed locus, so this is incidentally fixed locus of a torus. This is always smooth. If x is smooth, so let's assume it's smooth. And this is then the remark of smooth. Then the remark about it that this is smooth. smooth, but could be disconnected, but could be a bunch of connected components. Maybe call this Fi, the fixed loci. And if X is a vector space, which is most familiar setup for physical theories, and so then in a vector space or near one component, this would look like this. So then we take, so suppose we have one component of this fixed locus, call it Fi. And so if it's a vector space, it's just a vector subspace. And then what this Lagrangian would be? Well, that would be just the set of directions that attracted to this Fi. So there's some attracting direction, there's some repelling directions, and then since if my action is symplectic, then the number of repelling is exactly matched to the number of attracting, and then a general trajectory maybe I should miss the fixed locus altogether, goes something like that. So we have a very nice attracting manifold. I'll just write it attracting. This is the set of pairs. You have some point X and some fixed point F. So this is my point X, and there's a fixed point F here. And the condition is that the limit as A goes to 0, and this limit, this means choice of this limit. Sorry. Choice of this limit here. This is the choice of the chamber of the chamber there, of the chamber. Maybe call that whatever chamber. This chamber. And so the limit of A acting on X equals F. So that's what we'd like to have, except now comes the whole point, is that if X is not a vector space, if X is interesting, then of course the fixed loci, like I said, they will be smooth, but in general, there's no need to them to be connected. So if I have some global X, then I can have one component, maybe call it whatever F3, and then I have another component, call it maybe, just call this F2, and call this one F3. It's like the old joke about the, I'm not Gelfand yet at all, but old jokes. And so what can happen is that this attracting trajectory of one hits another one. So that's how. So this is nice Lagrangian. But not closed in general. It's closed if it's in a vector space, but it's in general not closed. So it's certainly a possibility. And so, so the example to have, of course, the simplest example to have, maybe I'll go back, and the simplest example to have in mind is like, well, maybe I'll do this example later. So if I take like T star of Grassmannian and then act by some torus in GLN, and then the fixed loci, if it's a maximal torus, the fixed loci are points, and the closure of attracting components are called conormal to the Schubert cells, and the closure of one hits another. It's certainly a possibility. And so this is, if you're, I will stop making any kind of allusions to physics in a second, but to put this in the context, what does it mean? That means if I have this trajectory between two different A fixed vacua, means this is in over complex numbers. This trajectory is really P1 connects them, right? So this is really CP1. So if I think about the CP1 as kind of an infinite cylinder, this is my CP1, and I can think of this as my space. Remember, we had some space C. So then over that we have some kind of, so there is an action of C star here. So just write down C star. And there is an equivariant profile of fields, which looks like, you know, maybe it looks like that. So this goes from one vacuum. So this you think there is some coordinates. These are kind of coordinates. These are coordinates on X, which is coordinates on X are all possible things we can measure in a steady state. And so there's a configuration of this field that is C star equivalent goes from here to there. So all of this, every holomorphic maps into C star is every holomorphic maps into X is going to be like, it's like a soliton in our theory. And in particular, there's this kind of soliton, which I don't know what they called. If somebody knows what they called it, maybe you can share. So there's some, and so this is, so we'll have to address this. And of course, so in other words, if I try to write down some sort of interface between one vacuum and another, we have to think about the fact that there's this kind of trajectories. And of course, what we need to do is solution is the oldest. Well, it's not the solution. Not the solution, but the way we're going to deal with it, what we will allow is that we allow these trajectories to. So if we hit a fixed point, then we allow the attracting. Then we allow a new attracting line, right? So this is if something was flowing to a fixed point, that fixed point can flow to another fixed point, and the whole line is allowed. And this is you know absolutely standard in the treatment of this sort of issues. And this is like you know, the breaking of Morse trajectories, breaking of geodesics, and so on and so forth. But so the way I drew it as if it continues straight is maybe slightly misleading. So the way it looks in local coordinates that I have at my F3, so at my F3, I have some repelling trajectory that's going to hit F2, and then there's some nearby trajectories. Maybe have them in yellow. There's some nearby trajectories that miss F3, but there is one that actually hits F3, and so then we need to allow this kind of incoming thing. And so this is logical. So if I have a family of trajectories, and one of them all of a sudden ends on this fixed point, then I should allow a trajectory emanating from that fixed point. Does that make sense? So it's like just, and so this brings the definition. So I can take, maybe I call it definition. The full attracting set is the set of pairs X and F, such that X is connected to F by a chain of attracting trajectories. So this object here is it's closed. And not only it's closed, in fact it's proper. So this is a subset in X cross the fixed locus. So it's closed. It's in fact proper over X. It's pretty clear. And so, but it is singular. Okay. I mean, it's a singular Lagrangian in the sense you can, like, if you look at its smooth locus, it's a Lagrangian, but it is a singular algebraic variety. So, you know, what you have to, maybe the picture to have in mind that if I have, you know, something like this, then in reality, these attracting trajectories, they're not going to hit this S3 in something nice. In fact, they're going to hit S3 in something very singular. They'll draw something like that. So the trajectories, if I start with a really nice trajectories, they're going to hit the fixed locus in some very singular way. Not only in a singular set, but even if it's a point, they're going to hit it in a singular way. And so then we'll have to continue it in some, you know, sorry, this is the wrong color. So we can, this will be a singular Lagrangian, but like I said, it is singular. Like for instance, so that's the, so for instance, so this is if I take, e.g., you can think about the example when X is T star Grassmannian, k-dimensional cell space and n-dimensional space, and I can act by A, which is a maximal torus, in GLN, and then this attracting manifolds. These are conormals to Schubert cells, and then this attracting full attracting set is some union. So these are their closures are, so this full attracting set. This is like a union of their closures. Right. So if I, you know, you hit some other point, and then you continue the attracting manifold of that point, and so on and so forth. So maybe, all right, attracting manifolds. So the full attracting set of some component Fi, that is the union over all the about attracting manifold. There's a natural order on what is attracting to what, and so then union over all Fj which are less or equal than Fi in this attracting order, we take the closure of this Fj. So this is a pretty singular variety, where this definition means this definition of something is less than something. It means that this actually belongs to the closure. And so the fixed loci are ordered by being in the closure of attracting set of another, and it's an exercise that if I have an action of action of a torus or any reductive group on a projective space, then and any subvariety of that projective space, that this is actually a partial order. There's no loops in it. Okay. Anyway, so there's some singular variety, and so this is kind of a basic observation. So it does not by itself class and cobordism. And a basic kind of result about this say the Schubert cells is that even if I take resolutions, then the cobordism class of resolution depends on which resolution I take. So cobordism class for resolution depends on resolution. Even in this, so this Grassmannian is the absolutely simplest example of what we're talking about, even in this simple case. So and so and in general seems like maybe resolution of singularities is not the way to go somehow. Anyway, this is not what we're gonna do. So what we'd like to put, so our goal, we remember at some point I motivated why the elliptic homology are important to us. So let's take that for granted and just say that we don't want a cobordism class. We want an elliptic homology class supported on this full attracting set. Where? Somehow canonical. We don't want any, of course, there's all some, but we want acanonical. Okay. And so let's just when one specifies wishes, it's good to be very clear as to what is it that one wishes for. So what is an elliptic homology class? So what is it? What's that? Sorry, what's that? And so this can be debatable, but this could be, one can make a long debate about what is that supposed to be. But we will take a very practical definition. This is what we. So for us, the elliptic homology class is just it's just some section of some line bundle on this elliptic homology. So in principle, so we can take like the centralizer. So in principle, we can take automorphism equivariant elliptic homology of X, where this automorphism means has to preserve this commutes with A. But to make matters simpler, let's just choose a maximal torus in here, and that torus contains A. So that would be so we have okay, we discussed what this object is. This is an object is some. This is an object of a. This is whatever it is. It's some scheme. This object here. It's a scheme over elliptic T-covariant homology over point. And so this is just a bunch of elliptic curves. So this is just elliptic curve raised to the power rank of that torus. Maybe more canonical, that's the elliptic curve tensored with the co-character lattice of the torus. Okay, it's a scheme. One can ask for a section of a line bundle. So this is in ordinary in cohomology or K-theory, those are rings, and element of cohomology, element of K-theory, it's a function of the spectrum of that ring. Okay. So now in elliptic situation, we don't have a ring. We have a ring, space. We have a scheme, and then we can, of course, we can ask for functions on that scheme, but that's a that's like a the projective variety, so there will be no particular interesting functions. And so the idea would be that instead of asking for a function, well, let's ask for a section of a line bundle. That makes sense, right? And so what kind of line bundles? So now what sort of scheme is it, and what kind of line bundles? Right, and so and what would be the strategy? So the strategy would be let's just go back here. Let's have let's copy this picture one more time. And so then, okay, this green one hits a new component at some point. We call it F4. So there's now the green one hits this F4, and then we take the attracting manifold of F4, and so forth. And so the strategy would be that we're going to construct this strategy. We will construct inductively. So since the whole manifold is constructed, the whole attractive manifold is constructed inductively, it makes sense to construct homological constants inductively. So we define. So I suppose we have. Remember that we have. So we have a partial order among the components of the fixed locus, and we can choose a linear order. So order components of the fixed locus by attracting by F. Well, we'll remind you what the order was. So this is by if the attracting manifold of some component Fi, the closure contains Fj, then this means that Fj is less than Fi. So we will order them. So we have F1, F2, F3, and so forth. So it means these are attracted only to. This is attracted here. This is attracted there. This could be attracted straight there. The attractions go only the one way. Okay. And so then we define Xn as X from which we take out all the attracting manifolds. So we take the union of from I greater or equal than n, the attracting manifolds of each Fi. Okay. All right. And so this is in particular means like the picture. So this is, for example, this whole set. This is X3. So this is we take something which is in F3 and attracted to that or below. And so this means this class, this attracting manifold of F2, this is a good manifold in, so this is inside of X3, this is closed. Closed, since we took out this, all of that we took out, so this is closed, proper over X. So this is some manifold we like, so this defines for us an elliptic homology class, we can define the Bordism class, whatever. And then if I take, if I want to now extend it to one step further, well, obviously X3 sits inside, so X3 sits in just inclusion into X4, right? So this is, so I apologize. So this is X3, it means we remove this. This may be a bad picture. We remove this to get X3. It's just inclusion. And so that means it induces a map. So if I have an inclusion or not, a continuous map between topological spaces. Well, it's inclusion, in fact, equivariant inclusion. A continuous map between topological spaces induces a map on elliptic homology. So I have a map from elliptic T-covariant homology of X3 into elliptic homology of X4. Okay. And so as we will see, this map is in fact, so this turns out to be this map here this is an inclusion of a closed set. So what we're supposed to, how we're supposed to picture this? So remember for projective space, we had elliptic homology looked something like a union of coordinate planes. It looks something like that. So this is for, like, if I have something like that. So this is for, so example, for X equals, well, in this case, T star P2, where this thing were each, and so this was each of this thing was in fact an abelian variety. So each of this was, so maybe take the torus, let the torus act be of the form with the action of a two-dimensional torus, say 6 like that. So equivariant homology, each equivariant homology of each fixed point is E cross E. So each of these pieces is E square. So this is isomorphic to elliptic A of a point, and they join together like this. There's a 3 copies of square the elliptic curve that copy like that, and so this is correspond to this corresponds to 0.1, and then 0.2, and then 0.3, something like that, or maybe And so then if I want the inclusion of the so these are maybe I'll draw a toric diagram. Not the best color for that, so like that. So I have a triangle like that. So this is now P1, P2, P3, and say attracting this 2 attracted here and that is attracted there. Then my X 3 that is T star P2, take out the attracting manifold of the 3rd point, and my X4 is the whole thing. And when I take out the attracting manifold of P2, that means I take out this piece, and so this means I take an inclusion. This is the map. This is the elliptic homology of, well, there's one more direction. So this I'm only doing so then there's one more toward direction, but let's just do A great. So then it's really right. So this is of X3 being included in elliptic homology of X4. Okay. So this is. And so then there is a very general problem in algebraic geometry. Geometry is if I have Z, let's just say scheme, and then there's an inclusion, just check Z prime closed subscheme. And if I have a line bundle, on Z, then there's a very general problem, kind of interpolation problem. The interpolation problem is extend or find extend sections of L from Bayer restriction to Z prime. So this is, for example, if I want to know polynomial of a given degree is determined by some number of points in like the old interpolation, this Z could be a curve and Z prime could be some number of points. And then I'm asking whether sections of some line bundle on a curve are uniquely determined by the restriction to some finite number of points. It's like the old interpolation. Maybe other familiar interpolation is like, for example, if I have, if Z is a surface, e.g., this I'm not going to, with the points, I'm not going to draw, but say if Z is a surface, and then maybe Z prime is a divisor in that surface, then sections of a line bundle are some other curves on the surface, so this would be, so this is our section, this is a section of L, so this is Z is surface, and this could be divisor. And it's a question whether a curve is determined by its intersection with some other fixed curve. So that's so suppose I give you the point where so in the surface I can ask the following question, like if I have a fixed curve, and if it's some fixed curve with some degree, and then if I have some moving curve with some degree, which means a section of some line bundle, then whether that section is determined by where it hits that Z prime. So then the absolutely general procedure to solve, begin to study that kind of problems is, well, by definition, we have an exact sequence. We have all functions on Z, structure shifts. This surjects to functions of Z prime. This is what it means to be a closed subscheme. It means I have surjection from the structure sheaf, and the kernel of that is the ideal sheaf, Z prime. Take this and tensor with L. So then we get what we're gonna get. We're gonna get here. We're gonna get L. This will surject to L restricted to Z prime. With the kernel, well, there's no better notation for that. I just write L tensor the ideal sheaf. And so then, if I want to know, interpolation is about the kernel. So interpolation, we want to know the kernel and the co-kernel. So there's, if I have a map of sheaves and I have a map of sections, H naught of L and H naught of L restricted to Z prime, right? So what's the kernel of this map sits in here, and the co-kernel of the map that sits by the long exact sequence that sits in H1. Sorry, kernel sits inside the global sections. So there's a kernel and co-kernel. So interpolation, in interpolation problem, we ask about these are conditions. This is existence of interpolation. Means which configurations in this picture here, which configurations of purple points can be induced by intersection with the section of L. So this is existence, and this is a kernel of that is uniqueness. And so kernel by the long exact sequence sits inside H node of this tensor with the ideal sheaf, and the co-kernel maps to H1 of this L tensor with the ideal sheaf. And so this is if we want uniqueness, we would like this to vanish, because if this is right, so this uniqueness means this has to vanish, and if this vanishes, implies existence. So that's general treatment. So now what is it going to look in our case? In our case, what was that? So let's just go back to this example. So what is that? What's that ideal sheaf? So the ideal sheaf here. So maybe I'll draw the opposite map on functions. So there is this map. Why don't I move this thing here so that we have this is positioned the way I'd like it to be positioned. So then there is there's a restriction of functions. So we have O of elliptic homology. Did I have A range elliptic homology of X3 maps to this map is restriction of functions O of elliptic homology. So that was a 4 X4 elliptic homology of X3. And so what would be, okay, every function, so since this is a closed subscheme here, every function here is a restriction of something there. So okay, this goes to 0. This restriction. And then what's the kernel? So which are the functions on this union which are go to 0? Well, that's pretty clear. So these are the functions on this thing. So function on this component which vanish along the intersection. So these are functions on the elliptic homology of just the fixed point that vanish. The intersection. This intersection with previously constructed things. And if you remember, we will go over this one more time. Don't worry about this. But if you remember what was happening on previous lecture, that is nothing but that is the Thom sheaf of the normal bundle to the attracting component of this F3. So this is if we add the cells like we were adding last time, and we'll go over that one more time. If you don't remember what was happening last time, it's okay. So, but the point is that in this induction, the ideals that we have to analyze at every point, those are ideals precisely have to do with the stone sheets of normal bundles. Okay, and so so let me get a drink of water. And so what we would like to have, we would like we want is the cohomology, the first cohomology of, or the first and the second cohomology of this tensor some line bundle L. We would like this to be 0 for I equal 0 and 1. So that would be something desirable. That would say that if this cohomology vanishes, that means every single thing before has canonical restriction. And so these are whatever they are, these are all cohomology of a line bundle on an abelian variety. Fact. So abelian variety in this case is in this case is the A-covariant elliptic cohomology of a point, which is just a product of elliptic curves. And so it's worth reminding ourselves, what do we know about line bundles on abelian varieties, and what do we know about their cohomology? So this is meant. So if by some strange coincidence all of you have just refreshed this in your memory, that's great, and then we can move forward. So if you'd like this to be skipped, then just you can write in chat. But I think it's worth repeating what this looks like. And so maybe let's general. So this will be general facts. So if let A be a abelian variety, then its Picard group is a group of line bundles that is I want to write a product, but it's not exactly a product. So maybe I'll write it as a union. So it's a union over all possible degrees. These are possible degrees indexed by the neuron severity group of your abelian variety, with line bundles of that degree. Oh, maybe you know what? I'll just try the exact sequence. So if I look at the Picard group, so this is the group of all possible line bundles, then this has a component of line bundles of degree 0. So pick 0 of A. Those are one way to define them, those are algebraically equivalent to 0. Zero have degree 0. Those are, so this embeds here, and the quotient, this is called neuron severity group. This is a discrete group. This quotient is discrete, and this is connected. In fact, this is another abelian variety. This is also an abelian variety by definition, called a dual, also an abelian variety. And the main result about the homology of line bundles, main fact, that if you have a line bundle of degree 0, and it's not trivial. So this is the pick series consists of all line bundles that can be put in an algebraic family, one of which fiber is a trivial line bundle. But so it can be put in the family with one of the fiber being a trivial line bundle, but it's not trivial by itself. Then all cohomology of that line bundle are 0. This is really kind of amazing. So this means these are line bundles of degree 0. They're in fact they're like characters. So if you think of this like these are like characters of your abelian variety. So this is what makes Fourier-Mukai transform work. So what makes Fourier-Mukai transform work is that if I have two different ones, L1, L2, two different ones. Then if I take all cohomology of the ratio, that is 0 unless L1 is actually isomorphic to L2. So they're like characters of group. They're just like orthogonality of characters. So this is what makes Fourier transform work for like analysis makes Fourier. So this makes Fourier-Mukai transform work. So then we need to know how do we describe the degree of a line bundle? So degree of a line bundle. So this is where degree. So the degree takes. This is where degree takes place. So then we need some language to talk about degree of a line bundle. Well, what's it going to look like? So what is the neuron severity group? So neuron severity group of a product of elliptic curves. So what's that? So we were interested in something like that. And we will talk about that, explain what it is for general abelian variety, but we need this case. And so, okay, so then we start with R equals 1. Okay, that is easy. every line bundle. So every line bundle on an elliptic curve is isomorphic to O twisted by some bunch of points. In fact, this is true for any curve, and this is taken modulo. It's taken modulo linear equivalence. And then, and so the degree is just summation of mi. And so this is an integer. And that integer is the neuron severity group. And in fact, somehow, what's remarkable for abelian varieties is that the Picard functor is represented, well, I mean, in the fancy language for algebraic geometry, is represented by a fine moduli space. Means, in fact, not only is parameterized line bundle, but there's a universal line bundle, which parameterizes all possible line bundles of degree 0. And so this is, and the way it looks for elliptic curve, E check is isomorphic to E. And then what we need is the universal family of, what we need is universal. So the universal family looks like this: universal bundle, universal line bundle over. So say in general you have, in general it says, in general it sits over A cross A dual. So this is universal, it's called Poincaré. And so we need a universal line bundle over E cross E. Well, it's just, so if E cross E looks something like that. So this is my E cross E. And I will take a divisor, which is the diagonal, and I subtract the two curves. So this is O of the diagonal minus E cross 0. Just write 0 without minus 0 cross E. Okay. So if I restrict to a point, this is, say, this is my base curve. It's my base curve E. And if I restrict to some point A there, then the bundle I'm getting here is O of A minus 0, where 0 is the 0 point, right? And it's clear that all line, it's well known that all line bundles of degree 1 of degree 0 have this form, and that's this universal bundle. Okay. All right. So now we can talk about what is peak. Sorry, not peak. Neuron severity group. Or in general, let's just talk about peak. Let's just talk about peak. What is peak of E cross E? This is R equals 2 case. Once we deal with this, when we're done with this case, then we can pretty clear will be the general case. And so, okay, so in E cross E, so this may be a question mark. So in E cross E, we have two things. So this is my E cross E. Already just drew it. And there are projections to each factor. We call them P1 and P2. And there's also inclusions of each factor, kind of E0 to 1, and iota 2. And so maybe this includes just exactly like this two things. Okay. And so corresponding to this map, I have a map from pic E square goes to pic E cross E, and then goes to pic E square again, where this map is the pullback by P, and this is the pullback by the inclusion. And it's obvious that the composition of these maps is identity. And so this is we only need to know what is the co-kernel of the, so what's the co-kernel? Or another way, kernel. What's in the co-kernel of, or in the kernel of iota star, right? And so if we take the quotient, so pic E square modulo pic E square, we can think of this are the line bundles. Line bundles trivial on the image, on this purple thing. Okay. That makes sense. Okay, what are those line bundles? Remember, I had, well, it's not I had, some smart people before me, but I'm just repeating what smart people before me discovered, is that there are two very important facts about the abelian variety. One is the vanishing of homology, and another fact that the Picard functor is represented. Means there's a and so in this case, what does it mean? Suppose I have a line bundle. So if I have such, suppose L is such line bundle. Suppose L over E cross E is such line bundle. So this is in particular, it's a line bundle on each of the factors. This means it gives me, so this means I have a family of line bundles on E parameterized by E. So it gives a map from E to in fact pic 0 of E, because the line bundle L is, since it's trivial on one factor, it's, so this is why is it 0, because this is because L restricted to 0 cross E is trivial. And so in particular, this E fits in a family of line bundles, one which is trivial, so this map goes to pic 0. And so then this map, well, we know that this is isomorphic to E. And then moreover, such that and this map takes 0 to 0 because L shifted to the other that is also trivial. So it means it goes 0, means this map, this goes to 0 to 0. If I have a map between between abelian varieties that takes 0 to some general fact. And actually, so I regret not having assigned exercises to this course. I think if you haven't seen this before, it's been a while since you saw it. I think it's a good exercise to go and prove the homology vanishing, to prove this fact. So if I have a map between abelian varieties, that takes 0 to 0 is a group homomorphism. So in other words, this says that peak of E square over peak of E square, this is home from E to E. Okay. So this is home from E to E. It's some abelian group, some discrete group. Always contains Z. Multiplication by n. May contain more if I have a curve with complex multiplication, but we're not going to worry about that. So we're not going to see those line bundles in this discussion. So in principle doesn't have, in principle E can have more homomorphisms if it has complex multiplication, but we're not there. We're not going to need this fact. And so this is so then in particular this says what? That if I take the neuron, then says, so this is says what? Says that the peak 0 of E, in fact in general, of any number of copies, that is just the same as the peak 0 of E to the r's power. So that's one conclusion from this. So peak 0 just multiplies. And neuron-Severi group of E cross E, that is the neuron-Severi group so maybe like E square. This is the square of the neuron-Severi group plus the homomorphisms from E to E. And the way to phrase it invariantly is that the neuron-Severi group of a square, those are the homomorphisms from E square to E square, which are symmetric. Symmetric meaning, so in general, so if I have a map between abelian varieties, so this is like if I want to, so yeah, what's happening here? Here I have, well, in this particular instance, this number was, that was just Z. That number is just Z, the 2 copies of Z. So I'm going to think of this as I have Z here, Z there, some sort of, whatever, some kind of homomorphism, we'll call it alpha, and here I put the alpha transpose. Where the transpose, that is the dual map. between dual varieties. So in general, how does generalize it? General, so the neuron severity group of any abelian variety, this is the home from the abelian variety to the dual abelian variety, which is symmetric. Because for every symmetric with respect to what? And if I take a map from a abelian variety to the dual variety, then there's a transpose. Well, if I transpose a map between, well, if I take the transpose, I get map between duals, so it goes to the same space. And symmetric means that it's invariant under this transpose. So this is the so in particular, if E is generic, like I said, we don't need any kind of assumptions on E, but if E is generic, then this is just then the neuron severity group of E to the R. These are just symmetric matrices. Trick R times so. Maybe I'll write. Sorry, let's just take a general statement. So in general, so if I take the neuron severity group of, or maybe so funny, write this something in general where there's right adjacent is a more general statement, so maybe I'll remove that in general. So the neuron severity group of R copies of S always contains symmetric R by R matrices with values in Z. So these are the same as integer quadratic forms. The same as integral quadratic forms. And this equality, I mean, this is equality if E is not CM, we will never need it. So we just enough. All our line bundles will always, the degree of all of our line bundles will always land here. So this is where degrees of this degree will always land. Maybe one more general thing to say is that another general remark about this map here. So if I have a line bundle, if L is a line bundle on A, and T of A is a translation by A map. So if I have a map from A to A, where some element B goes to A plus B, then if I have T of A pulled back by this map and I tensor it with L, inverse, this is a map from A goes to pick 0 of A, so it's a map from A to A check. It's this map. This is symmetric map. This map is the degree. So this is homomorphism. This is degree of A. And so this is an exercise do this for E, for E itself. Just check that this agrees with our previous definition. Anyway, why are we, so going back to this side of the story, why are we only worried about integral quadratic forms? Well, it's because we're only worried about things like Tom bundles. So if I have some fixed locus, maybe I call it F, just in general. Suppose some have some manifold Y, and I have some vector bundle over it, call it V. And suppose I have an action of A, which is Ajax trivially. This is A is fixed by A, but A acts on the fibers. A acts. Then remember we talked about this theta of V, which is section. So this is kind of like which is section of which product of theta functions of its Chern roots is a section. So the way this is defined is that this vector bundle defines a map. So a map from elliptic A Karenka homology of Y, which is since A is X trivially just some number of copies of an abelian variety. This is gonna go to elliptic GLR or UR Karenka homology of a point. And where so this is the Rth symmetric product of E. So this is where this point V1 VR lives, or maybe called R. And so then we pull back so then this maybe call it C, and then this theta of V is the pullback of the O of the theta divisor. The theta divisor is one this is where one of the PI's is equal to 0. Right? And so then since this A acts A, we want to know what is, so this is, so we can A acts trivial, so we might as well consider the inclusion of a point here, and we can ask what's the degree, since what's the degree of this bundle pulled back here. So the degree, maybe you can degree of just inclusion of any point doesn't matter, since the degree is, so this is, so we fix some point y. The degree is not going to change. So the degree of, we take iota pullback of this theta v. So this is degree. So this is some line bundle on the abelian variety, and so then this is the same as the degree of well, I have to have two pullbacks. So pullback by iota, pullback by of this here. And so now I need, and so this would be saying, so here I have some coordinates. And so what is this map? So this map is here I have some coordinates. So maybe coordinates are A1 through A whatever rank. Maybe call it N. And then they act in the fiber over my point by some act in the fiber. So maybe this say point this are in my actual. So this may be A. These are coordinates in my actual torus A. Act in the fiber of V over a point. By some monomials. There were A to some power, maybe call it Wi. And so then the degree of a product of theta function, I'm asking what's the degree of a product of theta functions of there's some monomials Wi? Okay, so that is first of all the sum of the degrees. But each one, the degree of each one, we decided has to be an integer quadratic form, which is pulled back from codimension 1 subtorus, and there's a, so what it is just summation of Wi squared. In other words, so this is what we've proven is that the degree, if I have some vector bundle and restrict to a fixed locus, I want to compute the degree of this theta V that has to sit, this is some element in where? This is, first of all, there's some particular characteristic class, which are the, sorry, these are the, I changed these to W's first at some point, I don't know why. This is sum of Chern root square, so this is some particular characteristic class. This is, if you want, this is like C1 square minus 2C2 if you want. So this is particular class of the vector C1 of V squared minus 2C2 of V. And so this is an element. This sits in symmetric square of characters of my torus A. And the symmetric square of characters of A, that is the neuron Severi group of elliptic curve all times. Well, maybe not equal, maybe it's contained in of elliptic curve all times co-character. So that's the that's the computation. So the computation is that if I want to know, I have geometrically defined problem about interpolation, means I have to know homology of some line bundle. I have a way to compute what the degree of that line bundle is, of any line bundle of this kind. It says this degree. And then so that's and then I have to arrange things so that I need to arrange things so that this that the degrees works out. So that's, well, anyway, that's the plan. That's how we're gonna proceed. Well, for a change, I'm more or less on time today. So that's do we questions? Not a single question? All right. That's a little bit depressing, but anyway, I tried my best. Then I thank everybody, and we'll see you next week.